Assalamu alaikum and welcome to our project presentation for discrete structure. Our project is titled as Temporal and Category-Based Price Similarity Network Analysis. In this project, we didn't just look at inflation number, we used discrete mathematics, specifically graph theory, relations, and partial orders. To model the economy of Pakistan, we analyzed CPI, Consumer Price Index, data from the Pakistan Bureau of Statistics across 17 cities and 7 product categories for over 3 years. Our goal was to determine which cities are economic hubs, which are bridges, and how these relationships change over time. We were a group of 3 members, Ali Bazmi, who handled the data extraction and the advanced weighting schemes. Hassaan built the graph theory, algorithm, and partial order verifications. Taha created the advanced visualization and interactive interface. Let's dive into the code and the math behind it. First of all, the libraries and setups we used. We use Python because of its powerful data science ecosystem. Here are the specific libraries that we used. Pandas. This is our Excel handler. We use it to read the CSV files, clean it, and structure it into data frames. It allows us to perform pivoting and aggregation easily. We use NumPy for crucial mathematications. We calculated cosine similarity using NumPy library. We use Network X library that allows us to convert our data into nodes, cities, and edges similarities. We also use Matplotlib and Seaborn libraries. We use them to generate heat maps and network graphs. We also use Rich and Cautionary library to create interactive CLI menu, progress bars, and beautiful terminal outputs. One of the biggest challenges that we faced was data was not formatted. The Excel files were inconsistent, headers like Islamabad with having hyphen and next line between it, or Karachi having spaces in it. So what we did, we implemented a robust extraction pipeline, which you can look at by looking at the function normalize text for comparison. It strips all non-alphanumeric characters, spaces, and new lines, converting everything to lowercase. Secondly, load all Excel files. This function iterates through every file in our directory. It extracts prices for 51 specific items across our 70 canonical cities. It finds the header row dynamically. It creates a price vector. It then passes this data to aggregate yearly item means, which smooths out monthly seasonality volatility by averaging price over the year. The first one was equal weighting, where each centrality measure is treated equally. Secondly, we use correlational based weighting that computes pairwise correlation among all centrality matrices across cities. Thirdly, we use category importance weighting and assign a category weights proportional to their economic importance or CPI contributions. The fourth weighting scheme which we used was entropy-based weighting that shows that a measure with higher variability across cities carries more informational value.
Mathematical modeling and graph construction. Now for discrete mathematics, we model prices as vectors. We use the function as mentioned in our code, compute cosine similarity. This uses the journal cosine similarity function as we studied in the discrete mathematics. Now the question arises why we use the cosine similarity function. Euclidean distance would be biased by the raw price levels as given in our Excel sheets. So cosine similarity measures the pattern or angle. If prices in Lahore and Karachi rise by the same percentage, cosine similarity treats them as identical. Normalization. Before this step, we use a min-max normalize function to scale all the prices between 0 and 1. So expensive items such as petrol don't overpower cheap items such as salt. We build a function named build adjacency, which is mentioned in the code as follows. Here we define our relationship and use a similarity threshold, which was initially very low. At low value 0.65, we had a very dense and populated region. So in order to optimize, we used high sparse similarity factors such as 0.85, where the links and the relationships were very low, less than 15. So to optimize and further moderate the code, we used the similarity factor 0.75, which had a very balanced effect. However, what were the findings? When we use the similarity factor 0.85, it revealed the backbone of our economy. We found that utilities are very stable at this threshold, while food categories break connectivity. Now, centrality measures and weighting schemes. Once we have our graph, we need to know who is important. We calculated four matrices using the network X. First one is degree. It is a direct connection. Lahore consistently scores high here because it represents the stranded Pakistani market. Closeness. It represents how fast the price shock travel. Betweenness. This is the key. It measures the bridge cities such as Multan. Our code identified Multan and Faisalabad as high betweenness cities. They connect the agricultural south, Sindh, to industrial north, Punjab. Eigenvector. This represents the elite club. Islamabad scores high here because it connects to other major hubs. Entropy-based weighting shifted our ranking. It pushed Multan up the list because it has a unique high variance between a score, highlighting it as a strategic logistic hub.
Visualization and temporal relations. We visualize these results using a custom function visualize network colorful. The visuals explained. Number 1, the nodes. The circle represents the cities. Number 2, node size, proportionality to the degree centrality. Bigger the nodes, more the connections. Node color. A gradient purple to yellow represents the betweenness. Yellow nodes are the bridges. Number 4, edge color represents the similarity, strength. Red and warmer edges are more stronger. Let's talk about the temporal relations. We also look at the time and created the temporal relations. We created the temporal relations for the year 2023, 2024 and 2025. Let's move towards the Hass's diagram. We also generated a Hass's diagram. The Hass's diagram we generated was to visualize their partial orders. And what was the interesting fact there? The interesting fact was that we found a soft subset was needed with a tolerance of 0.2. Utilities showed a perfect chain implying that the transitivity factor is being followed, meaning that the market structure is rigid. Food frequently broke the transitivity, showing the volatility. So, what did all this code tell us? Number 1, the hubs. Karachi, Lahore, and Islamabad are consistently the top 3. They are the market leaders. Next is their bridges. Multan is a critical connector in our betweenness heavy weighting scheme. Multan jumped from rank 5 to rank 2. This suggests that if you want to stabilize the price nationwide, you must control the supply chain in the Multan. Next is that the cities like Khuzdar and Bannu are often isolated, meaning that they have the degree 0 at higher threshold, showing that the national prices policies might take longer to reach them. Category dynamics. Clothing prices showed only two temporal relations, indicating it's a high volatility market compared to the regulated sectors like transport. To summarize, we successfully used discrete structures to turn messy raw data into mathematical model of Pakistan's economy. Extra features that we implemented include 3-year analysis, interactive CLI, a robust menu system using rich, advanced weighting, specifically entropy and correlation based weights, which were not explicitly required but added a significant depth to the project. Fuzzy matching to handle data inconsistency and automatically. This project shows that the city influences isn't just a number, it depends on whether your value of connectivity degree or the strategy betweenness. Thank you for watching.